an AI-generated post for your viewing pleasure. Conquering catastrophic overfitting. Advancements in adversarial training. What if I told you that the very defense mechanisms we rely on to protect our neural networks could be sabotaging their effectiveness? New research unveils the hidden pitfalls of single-step adversarial training, revealing how catastrophic overfitting threatens the robustness of AI models. But fear not! An innovative approach promises to redefine our strategies for training models and fortify them against malicious attacks. Before we embark on this exploration, let's set the scene. We'll unfold the critical findings of this study that will ultimately question what we understand about AI vulnerabilities today. Artificial intelligence has revolutionized many aspects of our lives, from facial recognition to automated customer service. But lurking behind these advancements is a significant concern: how susceptible these systems are to adversarial attacks. A well-placed perturbation can fool AI into making incorrect decisions, leading to dangerous consequences. Researchers are working tirelessly to enhance the robustness of these systems, but new findings suggest that existing methods might not be enough to keep AI secure. Today we're diving into a fascinating study titled Taxonomy-Driven Fast Adversarial Training, which tackles this very issue. This research uncovers the challenges of catastrophic overfitting in single-step adversarial training and presents an intriguing new approach to enhance AI robustness. The idea is to systematically improve how we train neural networks so that they can resist those crafty attacks. So, what is adversarial training, and why does it create such significant concerns? Let's get into it. Adversarial training is a method used to improve the resilience of neural networks against adversarial examples inputs, modified slightly to mislead the AI model. Two approaches exist: single-step adversarial training, which generates adversarial examples using a single gradient calculation, and multi-step adversarial training, which iteratively fine-tunes those examples over multiple steps. The focus of today's discussion will be on single-step training, which has become prevalent due to its efficiency. However, there's a catch. Single-step training often leads to a phenomenon called catastrophic overfitting, (CO), where models perform well during training, but fail miserably on unseen data, especially under multi-step attacks. It's crucial for you to understand these concepts as we proceed. With this foundational knowledge, we can explore how the newly proposed methods can transform the way we safeguard our AI systems. Next, we'll break down the technical contributions of this study so you can grasp the innovative methods proposed by the researchers. The study begins by addressing the concept of catastrophic overfitting, (CO.AU). It's a phenomenon where a model becomes exceptionally good at defending against specific types of adversarial attacks during training, but crumbles under pressure when faced with new, unexpected threats. By recognizing that factors such as adversarial example, A, variability contribute to this phenomenon, the researchers craft a fresh angle for advancing model robustness. The authors introduce a taxonomy of adversarial examples, categorizing them into 5 distinct cases based on their classification and misclassification. For instance, in case 1, a clean example is correctly classified, but its corresponding adversarial example is misclassified. By mapping the occurrence of these cases to the training process, the researchers can better understand company. Building on these findings, the researchers propose taxonomy-driven fast adversarial training, TDAT, which incorporates 3 key elements: batch momentum initialization, a new loss function driven by taxonomy, and a method for dynamically relaxing labels. These components work together to improve the model's robustness and stability without incurring heavy computational costs. However, it's essential to note that the paper may underestimate the practical challenges associated with implementing TDAT in real-world scenarios. Although the authors assert that TDAT enhances robustness against adversarial attacks, they do not fully account for the noise and variability present in real-world datasets. This complexity can complicate the application of taxonomy-driven techniques, potentially leading to inconsistent results across diverse environments. What's particularly appealing is that TDAT shows improved robustness across popular datasets CIFAR-10, CIFAR-100, Tiny ImageNet, and ImageNet 100 outperforming previous state-of-the-art adversarial training methods. By leveraging batch momentum initialization, the researchers stabilized training and enhanced the diversity of adversarial examples produced. But they need to address varying conditions across datasets in their analysis, which can critically impact the interpreted performance gains. Additionally, the implementation of batch momentum initialization introduces further variability. The formula for adversarial perturbation relies on clean examples initialized with momentum perturbation, which may not yield the desired adversarial examples consistently, leading to discrepancies in performance that practitioners must be wary of. The introduction of label relaxation allows for a more gradient-friendly approach, accounting for misclassified examples that might otherwise cause instability in neural networks. Now, let's discuss how these advancements fit into the broader research environment and their practical significance. Now, the significance of this research extends beyond simply addressing catastrophic overfitting. The innovative taxonomy-driven strategy opens doors for future exploration in adversarial training. By understanding which types of examples lead to overfitting, researchers can better tailor training methods, potentially leading to breakthroughs and defending against increasingly sophisticated attacks. Moreover, the findings surrounding the imbalance in adversarial example generation remind us that adversarial training has broader ramifications in machine learning. This study's approach highlights the potential to integrate cooperative learning across models, which could ultimately create a network of AI that learns resilience against threats collaboratively. There's also an exciting implication here. The findings may usher in a broader conversation around how adversarial training can be enhanced in multi-model systems. Could we develop a collaborative approach where different models learn together from shared adversarial experiences? This could create AI systems that are not only resilient, but also adaptable to unexpected threats. However, there's an important caveat. The authors primarily focus on robustness against projected gradient descent. As noted in the introduction, single-step methods gain significant attention as a research hotspot due to their effectiveness and efficiency. This focus raises concerns about the model's long-term reliability, because it doesn't sufficiently address the impact of a broader range of adversarial attacks that neural networks may face in real-world scenarios. We must ensure that the results of this study translate into tangible benefits without the constraints of computational cost limiting accessibility. The complexity of the proposed methods necessitates significant computational resources, something that practitioners in less resource-rich environments may struggle with, raising questions about the real-world applicability of these findings. In conclusion, this study has illuminated a vital area of concern in adversarial training, catastrophic overfitting. The introduction of TDAT, with its taxonomy-driven strategies, offers an innovative way forward, making neural networks more resilient to new adversarial attacks. The outcomes of this research show us that by rethinking adversarial example management, we can improve our model's robustness and stability dramatically. However, for this innovation to be fully realized, practical challenges must be addressed, including the variability in real-world data and computational resource demands. We have a long way to go in ensuring the safety and reliability of AI systems, but studies such as this provide a clear path for future advancements. What do you think? How can we push the boundaries of adversarial training even further? Share your thoughts in the comments below, and don't forget to subscribe for more in-depth discussions on the latest AI research. Until next time, keep pushing the boundaries of knowledge.